Hello and welcome to our series for operating iNano's Nanoindentor. In this video, we're going to explore how to review and interpret the data taken on Fused Silica. Outside of the video, I performed 10 tests on this substance, so we're going to take a look at what we have. So right now, we are in the InView Review Data application. Using this icon here, what I'm going to do is I'm going to scroll over to Sample Data and Open, so I can choose the data set that we have over here. Let that open. So now I'm just going to let everything load up. We see one of the tests here, but in order to see an aggregate of all the data, what I'm going to do is I'm just going to hold the left mouse button, create a box, and capture all of the data points over here. Now that they're all being shown, there are two things to pay attention to: the precision and the accuracy of the data set. For precision, the most important thing to pay attention to is to look for any tests that are very clearly outliers like the others. In this case, we have two outliers. So we have this dark blue and this light blue line. So looking at the left corner over here, we can identify these two sets as test 1 and test 10. Looking at the other data, the standard deviation appears to be relatively low given how close the data set looks to each other. So any tests that are extremely off can simply be deleted by just selecting these two. So what I'm going to do is I'm going to hold the control button and then select on just test 1 and test 10. Go into the InView icon, select tests, and delete selected. It's going to press OK, and I'm going to allow for the system to recalculate all of the data. However, the more important factor is the accuracy of the data set. Since fused silica is a very well-known and studied material, it is commonly used to double-check data to make sure that the tip is fully calibrated and operating in a predictable manner. On the screen, you'll see a summary of the ways to determine if the data collection taken on your fused silica is viable. If your fused silica data does not follow the parameters shown, then you'll need to perform a tip calibration, which will be shown later in the video. According to nanomechanics, the average modulus should be in the range of 71.6 and 71.6 to 72.4 GPa. So what we're going to do now is we're just going to create a box here so that we can zoom into the data, and then we can look at what values we have. So if you look at this bottom left corner over here and you look at the y-axis, you can see that the majority of the data that we have here, it's very close, but it's not technically within the range of the modulus that we should be getting, as it seems to be a little bit higher. And what we're going to do is we're going to go over to the Hardness tab, and we're going to do the same type of comparison. So we can see now that it's supposed to be between 9.3 and 9.7 GPa. This looks okay, but at lower depths, the data isn't exactly how it should be. At least the good thing about when looking at these two data sets is that we see that the standard deviation between the two is relatively low, so that's at least good. So now that I've finished going over the fused silica data, let me show you how to perform a tip calibration. Tip calibrations are performed to compensate for the variable degree of imperfection in the geometry of the tip, along with its related load frame stiffness. Typically, these are performed when a new tip is being used or when the current tip has been shown to be worn through repeated usage. Although the current fused silica data doesn't really need a calibration, it's still very useful to perform one on here, especially as we start looking into the lower depths, because we want to make sure that we have the most precise data that we can using the best possible tip possible with the equipment that we have. Note that this procedure only pertains to the Berkovich tip. Note that with this Nanoindentor, because it's used by so many different people, it runs a lot of different methods on a wide variety of materials. So it's in your best interest to always be updating the tip on here to make sure that you have the most precise data possible. Although it was already completed, before you perform a tip calibration, you want to make sure that all aberrant tests on the fused silica data set are cleared. So in this data set, it was test 1 and 10, so we got rid of those data sets. So what you can do after that is you go over to the InView icon over here, click on Tips and Settings, then go to Easy Tip Calibration. So what you're going to be doing in this menu, all you got to do is just press the big Calibrate button. And what it's going to do is it's going to recalculate the tip based on the current data set that we have here without any aberrant tests. So it says that the tip calibration succeeded, so what we're going to do is we're going to just press Accept here and then allow for it to just recalculate all the tests that we have. There we go. So now the system is going to just use the newest tip calibration and load frame stiffness parameters to portray all of the data. So now our data is looking much nicer towards the lower depths of penetration within our fused silica samples. Just know that when you switch over to another data file that you want to look at, like let's say you want to actually look at your sample and you want to make sure that you're using the correct tip, just go over to the InView icon, Tips and Settings, and then Machine Settings. And then make sure that your tip that you're using is selected at the top. The tip that you create will be named with the strain rate and the date, so it will be very easy for you to just select that and then press Save and close. Let's look at the revised data set now. On top of being within the range, the data set is now calibrated towards the lower penetration depths. So what I'm going to do is I'm going to just zoom in there by creating the box. While it may not seem apparent, getting the tip calibrated at lower penetration depths is absolutely essential for the analysis of other samples that we have. Once we get the tip calibrated for lower penetration depths, then we will be able to have a higher degree of confidence in the data on our samples within a comparable range. So for example, let's say that I wanted to look at a silicon wafer in the 20 to 50 nanometer range, so kind of over here. So in order for that data to be good and correct and to be useful, you need to make sure that the tip calibration from the silicon data within this range is extremely accurate. So while it may look like it's kind of all over the place, the average of which is if you drew a line, the average of which would stay kind of along this region over here. So what I'm going to do is I'm going to zoom out now by just double clicking on the left mouse button. So in the next video, I'm going to move on to the annealed steel data set and show you how to review and present the data being taken. Thanks for watching, and see you next time.